Welcome back. This lecture series, which is just going to be one lecture, is going to be on Markov chain Monte Carlo. And we're going to be talking about the Metropolis-Hastings algorithm. And in short, this Metropolis-Hastings algorithm is going to be an algorithm to create a Markov chain that has a desired probability distribution. And the neat thing about this algorithm is that all you need is going to be able to sample a uniform distribution and be able to sample any Markov chain. And the only technicality is that the Markov chain has to be ergodic and it also has to have the same number of states as the distribution that you want to sample. But in any case, this Markov chain Monte Carlo, or in general Monte Carlo uh, methods, are used as it's going to be used to approximate certain expected values using random sampling. And if you if you have the interpretation of expected values to be integrals, then this is a numerical approximation of integrals using random sampling. And in more specifically for Markov chain Monte Carlo, you use a Markov chain to approximate certain integrals. So this is like the rough big overview of what Markov chain Monte Carlo is and Monte Carlo methods and the Metropolis-Hastings algorithm. And in this lecture, what I want to do is I want to start with something very specific, a very specific example, and see how to implement the and I'm going to implement the Metropolis-Hastings algorithm for that Markov chain. And um, I'm going to look at this specific example, and then it generalizes fairly straightforward how to do this in general for any distribution. And I'll give the generalization for any distribution, and then I'm going to move on to the theorems related to this. And this is going to be the more of a complementary lecture to the chapter 5 in the textbook by Dubrow. Um, the proofs in the Dubrow book are left out, but it has a really great discussion of applications of the Metropolis-Hastings and several examples that are great to look at. And instead, in this lecture, I'm going to focus more on the proofs that are left out. And this is just out of completion. I find the proofs fairly interesting, although they're just a tad bit technical. And at the most technical points, I'll just sketch the proof. But it's it's nice, it's interesting to look at the proofs, and it starts to give you a hint of the technicalities or some of the issues behind the algorithms. So we'll start with a specific example, generalize, and then look at the proofs. So let's look at the problem. We have this bias coin with probability P of heads and probability 1 minus P of tails. And actually, I think throughout the um, lecture, I'm going to have that I'm going to set P, or 1 minus P is equal to Q. So I'm not sure if I wrote it anywhere else, but if you see a Q, then just know that it's going to be 1 minus P. And we have this bias coin, and the idea is in real world applications, how do we sample from this bias coin? Aside from somehow getting our hands with a coin that has this bias, how can we do it? And more specifically, the question really means that how can I create a sequence of heads and tails such that it corresponds to this bias of this P? And this is an interesting question to do simulations, for instance. If you have a model and you have a probability distribution attached to this model, you want to be able to simulate it, and somehow you have to sample a certain probability distribution, and you have to make sure what this this that you're getting a good sampling. And for instance, if we look at this sequence of heads and tails, one question is, are we sampling from a specific bias coin? And if I had to guess, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 flips, and we have 1, 2, 3, 4, 5. So this would be, if I had to guess, the fair coin. This is a little bit scary because I just randomly wrote this out. I didn't mean it to be 10 coin flips, and I didn't mean it to be fair. So I guess I'm a pretty fair individual. Anyway, let's go to and again, this is a fairly simple example. So to actually sample a bias coin, it's actually not very difficult. And there's multiple ways to do it. The straightforward way is to actually sample a uniform distribution. And in practice, you're gonna to sample a random variable, any random variable, somehow you have to get your hands on sampling another variable and using that other variable to sample the random variable you're interested in. So in this discussion, this lecture, there's no way around somehow sampling something that we assume that we can sample some other random variable. And this one is sampling the uniform distribution. So we assume that we can sample a uniform distribution on the interval 0, 1. And in particular, we have a sequence of random variables, x1, x2, and so on. They're IID and they have uniform distribution. So we can sample, we have these random variables that have this uniform distribution. So to then sample a bias coin with the probability P of heads, then what we could do is we can introduce this random variable yi, which we can say it's heads if xi is less than or equal to p, and if it's tails, if xi is greater than p. And you can check that this random variable will have the desired probability distribution. So it's a straightforward computation that the probability of yi equals heads is the same as the probability of xi less than or equal to p, which is equal to p. So this is just the simple, straightforward way to sample a bias coin. And this is good to just kind of like set the background of how you can sample a random variable and other methods to do it. And this is the straightforward random variables. You can do it this way for straightforward distributions. And in particular, if you're actually going to sample a Markov chain and you're in substate I, and you can go to different locations, J1, J2, and so on, JK. But essentially, the way you sample that is you can sample a uniform random variable, and if it's within a certain interval, you go here, certain interval, you go here, and a certain interval, you go here, according to the probabilities of going to each of these things. So you can think of being able to sample a uniform distribution. It's going to allow you to sample a Markov chain. But in any case, this is a straightforward way, but we're interested in something that can be generalized to any arbitrary distribution. This can be also done that way, but somehow in this case, you have to be able to know your probability distribution exactly. And in practice, the following method that we have, you technically don't need to know the probability distribution. You just need to know the proportion of the probability distribution. So somehow you can get away without knowing a normalization constant for your probability distribution and then sample the probability. So you in the next method that we show, you can actually get away with not knowing the probability distribution you're sampling from, but just know part of the information. So you just need to know the probability distribution up to a multiplicative constant. So it's a much stronger method to sample this distributions. So this is sampling using a Markov chain. So in here, now we're going to assume that we can sample from a Markov chain xi. And in this case, I want to sample again heads and tails with two states. So I want to sample a Markov chain that has two states. And here I have that the transition rates or transition probabilities are given by these parameters. And really we should think of this as P1, 2, and this is P2, 1. And in here, I assume that alpha and beta are not equal to 0, and this is so that my chain is ergodic, that it's irreducible and aperiodic. And this is going to be a common feature that I'll need from all the Markov chains I use in the Metropolis-Hastings algorithm. So first we have that, and I'm also assuming that I can sample a uniform distribution, because technically to sample a Markov chain, the one way to sample a Markov chain is being able to sample a uniform distribution. Anyways, so now that I have the Markov chain X, I want to create a Markov chain YI that has the probability distribution of the bias squaring. And actually, it's not necessarily YI has the distribution of the bias squaring. It's going to be Y infinity. So the limiting distribution of the Markov chain Y is going to have the desired distribution. And so the Markov chain YI is going to have the matrix Q for transition probabilities. And I'm going to give you the transition probabilities for this transitions and I'm not giving you this transition probabilities explicitly, since this probability is just 1 minus this, and this probability is 1 minus this. And so for this transition from 1 to 2, I'm going to define it to be this expression. So it's going to be this ratio, Q over P, and which is going to be the probabilities of heads and tails over the ratio of these probabilities. So this quantity and the minimum of this quantity and 1. So if this quantity is greater than 1, then this whole thing is going to be equal to 1. If this quantity is less than 1, then this whole quantity is going to be equal to this. And then I'm going to multiply it times P12. And similarly, here I need to color the 2's. And here I do the same thing. I flip this expression over here, and I have Q from 2 to 1. And again, I take the minimum of these two terms in here, and then I multiply it times P12. And my claim here is that the stationary distribution, or the limiting distribution of yi, is going to be the probability of heads, P. So essentially I'm creating a Markov chain with an arbitrary stationary distribution, since P, I can choose P to be anything. And the way that I do it is, first I construct any ergodic Markov chain, and from that ergodic Markov chain I can construct the Markov chain yi that has the specified distribution. So let me go through the proof of this result. This proof is in Debro, and it's essentially just a computation. First, we note that yi is ergodic, and this is by showing that these terms are not equal to 0, and this is not equal to 0. And by the choice of p and q, I guess I'm assuming here for p not equal to 0. By the choice of p and q, if p is not equal to 0, q is not equal to 0, so this is not going to be equal to 0, and we assume that p is ergodic too, so this is not equal to 0, this is not equal to 0, so you can check that all of these are not equal to 0, and you can check that it's not irreducible and aperiodic. So this is by the choice of our parameters. And since it's ergodic, then we have that the limiting distribution is equal to the stationary distribution. And then it suffices to show that that pi satisfies this identity, and here pi should be equal to the distribution of the coin PQ, and that it's time reversible. And this we can check it explicitly is if we assume that we satisfy this time reversibility condition, then we can check that pi is going to be stationary. So what we need to check is that what we want to show is that the jth coordinate of this pi q is equal to pi j. This shows that it's stationary, and we are going to use this identity. So first, by definition, the probability of j after q, after applying q to pi, is this sum. And now, term-wise, we have this identity, and we have this sum over I. So term-wise, we're going to change this, but I doesn't change. And we change this to this, and we obtain this. And now we have this summation. And since Q is a stochastic matrix, then we can factor this pi j out since it's independent of I. And then we have a summation over Q, and we have a stochastic matrix. And then the summation of Q over I is going to equal to 1, so we get pi j. So this is equal to this, means that pi is stationary. And since stationary is equal to limiting for ergodic, we have that this is the limiting distribution. So we set pi is equal to pq, the distribution that we're interested in. And what we want to show is this time reversibility property. And here, recall that the transition for I not equal to k, I not equal to j rather, is given by this formula. And in here, due to this minimum of these two quantities, we have to consider two cases, whether this quantity is less than or equal to 1, or if the quantity is greater than 1. So we work case by case. So in the case that it's less than or equal to 1, we have that Qij is equal to pi j over pi I times pj to I. And the rate qj to I is just going to be pj to I. And that's because the corresponding property in the minimum is going to be the inverse of this, and since it's less than 1, it's going to be greater than 1, and when you take the minimum is going to be equal to 1, and it's going to be 1 times this. So we obtain this. And now we can just check this identity straightforward. And we have pi I times q j to I. Using this identity, we say that pi i's cancel out, and you're left with pi j times p j to I. And then with this identity, we have that this is pi j q j to I. So we have the time reversibility property. And then the second case is the case where this quantity is greater than 1. And it's basically the same computation, but in this case now Qij is given by this and Qji is given by this for the same reasons as before. And we can do the computation again. Here, we need to color this I. And Qij is given by this, so it's just a simple substitution. And then Qji, we can write it this way. So we multiply by 1, which is this, and then we obtain this. So we have time reversibility here. So now by cases 1 and 2, we checked this identity. So we have that pi is the stationary distribution, and we have that pi is the limiting distribution. So this is going to be the limiting distribution 1, which proves our claim that the limiting distribution of y is equal to pi, which pi, since it's only 2 states, suffices to show this. And that's it. And that's the basic idea, that if we have a markup chain, an ergodic markup chain, we can reassign the weights so that we can have any limiting distribution that we want. And in this case, that's what we have. We have a target distribution that we want our markup chain to have, this distribution PQ, and we have some other markup chain, or we have a markup chain X, which is ergodic and whose limiting distribution is not necessarily pi, and in fact is most likely not pi. And so we have these two objects, and then we can transform this markup chain to this other markup chain Y that's going to have the limiting distribution. And really it means that we can use any markup chain to construct and sample a markup chain whose limiting distribution is going to be pi. And this is going to be the Metropolis-Hastings algorithm. And the way that it's implemented is that first you start your markup chain in some state I0, and now you do the following to sample yn. So yn plus 1. So assume you know the value of yn is equal to I, and you can sample xn plus 1, given that xn is equal to I, and you sample a random variable with uniform distribution on 0, 1, and then sampling xn plus 1, you have that it goes from I to j, and then you sample the uniform variable u, and if it's less than this quantity, then you're going to set yn plus 1 j. So if x jumps from I to j, and when you sample u, it's less than this quantity, you're going to set yn plus 1 equal to j. Otherwise, if this condition fails, then you're gonna decide not to jump. You're gonna reject the jump. So essentially what's gonna happen is that you're gonna be in your markup chain X, and you're gonna be in this state, and then you're gonna sample it, and if it attempts to jump to 2, before you move your markup chain Y to 2, you're gonna sample a uniform random variable, and if it satisfies this condition, then you're going to accept the jump. If it doesn't satisfy this condition, then you're going to reject the jump and just stay where you were. So this is the way, algorithmically, this is the way that we can implement the sample of Y, sampling Y, this markup chain. And really all you need to do is you need to be able to sample X and sample U. And then you can create this markup chain Y, whose limiting distribution is the distribution that you're interested in. And in general, this is the Metropolis-Hastings algorithm. So this is for any distribution. In here, you can do it for continuous distributions too. In here, I'm just focusing on the um, discrete probability distribution. And you're going to take a Markov chain XD, which is ergodic and has a transition matrix P, and define an acceptance function, which is this ratio. And you're going to introduce a Markov chain that moves from I to j if x moves from I to j and u is less than or equal to this acceptance function. So you're going to decide to move from I to j in this Markov chain. First, the x Markov chain needs to move from I to j, and then you sample a uniform random variable, and you have to check that it's less than this acceptance function. And here we'll have that. In here, what I want to note is that what I remarked earlier is that technically you actually don't need to know you only need to know pi up to a multiplicative constant. Because if you change this by alpha, add a multiplicative constant, and here the acceptance function, you're going to do alpha over alpha, which is going to cancel. So in practice, one of the reasons why this sampling algorithm is useful is because in practice, you're not going to you may not know the exact probability distribution. You may just know that the probability of a certain configuration is proportional to a certain value. And it happens in physics where you can just you know that the probability of a certain configuration is proportional to the energy. But then you don't know what is the sum of all the energies, and computing that is a difficult task. But you can sample that physical system using this Markov chain Monte Carlo method, this Metropolis-Hastings algorithm. So as opposed to the first answer that we gave earlier, where you just sample a uniform random variable, you actually need to know the exact distribution. But in this case, you only need to know this distribution up to a multiplicative constant. So this makes this method more powerful and more robust. And the claim here is that the limiting distribution of y, this Markov chain that we created, is going to be given by the targeted distribution that we want to sample. So this is the Metropolis-Hastings algorithm in a nutshell. And for a very simple case, the proof of this is going to be the same as a proof for n equals 2, the case of the coin flip. And in practice, the way that you sample from pi is that you're just going to run your Markov chain y for a long time, and you run the Metropolis-Hastings algorithm. You run it for a long time, and then after a while, the sample is the outcomes from the Markov chain y, and this technically this only gives you, since it's the limiting distribution, this sample may not be exact as described here, but there's modifications you can do to get exact samples. And you can actually see this method in the textbook in the Bra in chapter 5. And also it also brings another question, that how long is long enough to wait for time to be for the distribution of the Markov chain y to be close to the limiting distribution, and that's also another technical question. It corresponds to the second largest eigenvalue of your Markov chain. But those, you can read about that in the Bro, and those are more technical aspects that are covered in the textbook. And instead, I want to go more into this following claim, which is stated in the book without a proof, and which is one of the main applications of this Markov chain Monte Carlo or Monte Carlo methods, where you want to compute the expected value of a function of a random variable. So in here we have a random variable, it has distribution pi, and you want to compute its expected value, of g of x, and y is the Markov chain you obtain from the Metropolis-Hastings algorithm. Then you can actually compute this expected value, which you can think of this as an integral over some measure of this function, as doing this sampling of this Markov chain. And just sampling for a large amount of time, you can approximate this expected value with probability 1. And g here is just, since we're in the discrete case, is just going to be any function from 1 through n to r. So n can be here arbitrary. It's just the number of states of the random variable. So in here, this is going to be pi 1 through pi n. So I want to focus on this claim for the rest of the lecture. Here, I'll make this more technical, what I mean with probability 1, but this is the thing that makes it a bit more challenging to prove. We can show the, I don't know if you guys can hear that. The rice is done. It's the rice cooker with the song. Hopefully you can hear it. Anyway, so it means that for any sample, if we sample long enough and we take this average, then any sequence of samples is going to get me to this expected value with probability 1. So it doesn't matter if I get some weird samples, it's all going to average out and it's going to give me the expected value that I want. The weaker claim would be that on average, this sampling is going to give me the expected value that I want as the number of samples goes to infinity. So this is the weaker claim, and this is the stronger claim, that this is going to happen but with any sequence of samples of my random variables, of my Markov chain. But this claim says that on average, then it's going to be equal to expected value. And this is fairly clear how this implies this. You can just take the expected value and move it inside, and it's going to be, we're going to obtain this. But actually the way that we're going to prove this first claim that's stronger is we're going to first prove the weaker claim and then enhance it to prove this one. So let me first prove the weaker claim. Since we're working with discrete random variables, I can actually write the g function as the linear combination of indicator functions for some coefficient ci. And then we recall this following result. We proved it a few lectures ago on chapter 3 that we can take the expected value of this quantity, and by moving the expected value in with linearity, this is going to be the expected value of the indicator function, which is this probability function for some initial condition of y naught. I really should see I naught. And here the initial conditions are not going to matter very much, but and I haven't written it. Somehow it should be it should be given here that y0 is equal to I naught or something like this, but it's not very important. We have that if we move the expected value in, we have this conditional probability, and this is equal to the mth power of the the nth power of the transition matrix of the index from going from I0 to I. And since this is stationary, we show that this average is equal to the stationary distribution pi I. So this is a proof that we showed before, and since for very large m, this is going to be close to p infinity, which is going to equal to this pi I, and it's going to stabilize there. This is going to mean that this average is going to equal to pi I as t goes to infinity. And we proved this result earlier. So go back to the previous lectures if you don't remember it. I gave a little bit further discussion on this, but this is one of the technical results that we used before. And using this linearity or this representation of the function g, then we can actually prove the weaker result. So we write this expected value. We write g as a linear combination of indicator functions. We use linearity to take this sum out of that's given by writing g as a linear combination of indicator functions. And then we have this term of this expected value, which is this term right here. And by taking t goes to infinity, this is just the stationary distribution of y. And we have this summation, which is just going to be the expected value of x. So we have the weaker result, this weaker result. That this expected value, the expected value, oh, hold on here. I have too many 1 over t's. This is one too many. So this one. So in here, it's saying that on average, this sample is going to be equal to the expected value of g of x. And what we want to prove is something stronger, that every sampling of this is going to be in the limit as t goes to infinity is equal to the expected value. And this is a law of large numbers type result. And in fact, that's the approach that we want to take to prove this result. So let me recall the law of large numbers for IIDs, identically independent, identically distributed random variables. So assume we have a sequence of IID random variables with expected value mu and variance sigma squared. Yeah, right? Sigma squared, yeah. Sigma squared is right. Then the law of large numbers says that the limit of this average of samples is equal to mu with probability 1. And in particular, this is equivalent to saying that the limit as t goes to infinity of the probability that the difference that this average minus mu is greater than epsilon is going to be equal to 0 for every epsilon greater than 0. So any way that we sample this average, it's going to be arbitrarily close to mu as the number of samples goes to infinity. So that's what it means with probability 1, to have this limit equal to mu with probability 1. So it's equal to this precise statement. And so, and this we're going to be inspired by the proof of this result to prove the result that we want for Markov chains. But we need to adapt it somehow. But let's look at the proof for the law of large numbers. It's powered by Markov's inequality. And this says that for a positive random variable, we have this inequality, that this quantity is less than or equal to this. And here, one way to see this is that if this is the distribution. This is the, somehow assume that this is the distribution of your random variable, z, and you have some quantity here. Then the probability that c is greater to a is equal to this. And then, actually, let me just prove it. Expected value of c is equal to summation k is equal to 0 to infinity. I'm going to do it for the discrete case. P of c is equal to k. And then I'm going to say that this is greater than k is equal to a to infinity, k z is equal to k. So in here I've removed the terms from 0 to a minus 1. And then we can get rid of this. Delete. We can move this back up. And then the next thing that I do is that for k from a to infinity, I can lower bound k with a. K from a to infinity, a probability that z is equal to k. And now I can just factor out the a, and I have the summation k from a to infinity, probability c is equal to k. Just factoring out the a. And now I know that the sum of the probabilities on the right-hand side is just going to be equal to the probability that z is greater than or equal to a. And this is how we obtain Markov's inequality. And now, using Markov's inequality, we set z of t to be this quantity, the average of the samples minus mu squared, and which can be rewritten this way, that you center the samples and you average them and square it. And here you set a is equal to epsilon squared. And then you'll have that c of t here. I'm missing a 1/2. So we have that c, we have that c of t is less than or equal to epsilon squared. It's going to be the same as saying that z of t, absolute value, is less than or equal to epsilon 1/2. And so that's in here, it's greater than or c of t greater than or equal to epsilon squared is the same as c of t 1/2 greater than or equal to epsilon. And that's what we have here, epsilon squared. And then on the left-hand side, if we compute the expected value of c of t, you can actually see that it's going to be equal to sigma squared over t. So it's the expected value of this quantity. And in here, when you take the expected value of this quantity, you can expand this square, and you're going to have two types of terms. You're either going to have xi minus mu squared over t squared, which is going to give you sigma squared over t squared. And this is for I from 1 to t. Or you're going to have terms that are expected value of xi minus mu, xj minus mu over t. But this terms, due to independence, is going to be equal to 0. Because due to the independence, you can actually you can factor the expected value. So this is going to be expected value of this. And just move. And this is going to be expected value of this. And it's going to be 0 times 0. So the cross terms are going to cancel out to 0. And then we're going to have t of this terms. So that's going to be sigma squared over t. And then by moving this epsilon squared down here and rewriting this as this, we have that the limit as t goes to infinity of this quantity is equal to 0. So we obtain the law of large numbers in this case. And it's a fairly straightforward proof, and this is the proof that we want to mimic. The nice thing about this proof is that when you're taking the expected value of this quantity and you expand the square, then you have that the cross terms are going to be identically equal to 0. And we're going to try to do the same thing for the Markov chains, but we are not going to be able to have the cross terms equal to 0. But instead, we're going to show that the limit of the cross terms goes to 0. So this is how we're going to need to adapt this proof. So let's go through it. And here, for simplicity, I'm going to assume that my function g is just an indicator function. And what I want to show, in this case, I want to set zt is equal to this quantity. It's kind of like in the other proof where the random variable of interest was xi, and it was xi minus mu. So in this case, the random variable is this, and mu is just going to be the limiting distribution. And this is going to be my ct, and then by Markov's inequality, we have this identity. And what I really want to show is that, as I did in the other proof, is that this expected value goes to 0 as t goes to infinity. And that's going to establish the proof for the stronger claim. So let me start computing the expected value of c of t. And here, again, I have this power here, and I need to expand this square. And so the t squared factors out, and then I'm going to have two types of terms. This terms where the repeated terms, which is this squared, and then the cross terms, where I have m and l are not equal to 0. So we have two types of terms. This term is easy to compute or even bound, and we have that, first of all, this quantity, this indicator function is either 1 or 0, and this is a quantity between 0 and 1. So we can actually bound this quantity by 1, and the expected value of 1 is going to be 1, and then a sum over t is going to be t. So by bounding this by 1, we can do an upper bound of this by 1 over t, which we're going to take t to infinity, so this is going to go to 0. So bounding this term is easy. The next term that we need to bound is this cross term, which in the previous proof for IID random variables, this cross terms, we were able to show that the expected value is equal to 0, and that's how we obtain the proof. But in this case, we can't do that, and we need to figure out some other way to show that it goes to 0 as t goes to infinity. So let me focus on just one term at a time, and I have this expected value, product of this term times this term, and I expand. And I get this quantity, and by taking the expected value, I have that this is the probability that ym and yl is equal to I, and the expected value of this is the probability that yl is equal to I, and the expected value of this is the probability that ym is equal to I, and then this is just pi squared I. And in here, I'm going to write, so in here, this is where I start getting a little sketchy, but for L and M large enough, these probabilities are going to be roughly this is going to be roughly the stationary distribution I. And this is going to be roughly the stationary distribution of I. And for simplicity, I just take this approximation that these are going to be for L and M large enough. These are just going to be pi I and pi I. So I would have minus 2 pi I squared plus pi I squared. And then this is going to be, again, the probability of ym and yl is equal to I. And here I write it as a conditional probability. And I use the same type of trick here, and it should probably be approximation too. Or I assume that L is large, and for L large enough, this is going to be approximately pi I, the stationary distribution. So I assume that this is pi I, and then this is going to be the transition probability from L to M, and this is going to be the transition from I to I. In here, I assume that M is equal to L, but that doesn't need to be true necessarily. So, but for simplicity, I just wrote M. I assume M is equal to L, but if it's not, then the computation would be the same, and you just take the absolute value of M minus L. But in case this expected value for this term, we can approximate it by this quantity, pi I and this. And we want these terms are not going to be exactly 0, but we want them to go to 0. And the observation here is that if M and L, if the difference between these two indices is large enough, then this is again going to be approximately pi I. And then this is going to be approximately 0. So this is kind of what we want to do. We want to get this superscript to be large. So we look at all the terms now, the summation of all the terms. We simplify it using the previous slide. And here it's the sum over all terms Lm such that L is not equal to M and less than or equal to T. And again, T, we're going to take it to go to infinity. And then we're going to introduce a K, which I write explicitly, or I describe more explicitly in the next slide. But in here, I decompose the sum into two types of terms, L and M, which are not equal to each other and are a k distance apart at least, and L and M, which L is not equal to M, and their L minus M are close. The distance between L and M is at least k, or at most k, so they're close. And here I'm actually choosing k with the following property, and it's that for every delta greater than 0, we're going to have a k sub delta such that this transition probability is going to be close to pi I. The distance between this transition probability and pi I is going to be delta, at most delta. And this is going to be for any k greater than or equal to this k delta. And this is true because we have that pi infinity ki, or that limit of pk I is equal to pi I for k goes to infinity. And this is because that's pi I is the stationary distribution. So this is actually how I choose my case. So the indices are far apart here, and the indices are close. And when they're far apart, they're going to be the difference between these two is going to be roughly pi delta, at most delta. So I can do an upper bound of delta. And when they're close to each other, then I can bound this by 1. So because this is a number between 0 and 1, and this is a number between 0 and 1. So this is 1. So in here, I can bound this by delta, and I can bound this by 1. And so now in here, I just count the number of terms in this summation. And this is going to be, I can bound it above by t squared terms. That's a overkill, but it's good enough. And in here, I can bound it by k delta times t. And now when I divide by t squared, I can bound this whole summation by pi I delta, which comes from this divided by t squared, and pi k delta over t. And in here, we have this bound. And it's important to note here that this k delta is independent of t. So this bound, this k delta is going to be independent of t, and it's going to be some fixed large number. So when we put everything together, we have this bound for the expected value of ct, 1 over t coming from the repeated terms, and this bound coming from the cross terms. And then we take t goes to infinity, and we see that the upper bound as t goes to infinity is going to be this pi I times delta for any delta greater than 0. And this means that we can make delta arbitrarily small, and this upper bound is going to be arbitrarily small. So that means that in the limit as t goes to 0, this expected value is going to be equal to 0. So this is going to now, by Markov's inequality, this is going to be the upper bound. This is going to be the upper bound of this, which is going to be 0, and this is going to establish the stronger proof. And this is fairly technical, but this result, this stronger proof result, this law of large numbers for Markov chains, is a very interesting application, and so I wanted to go through it in detail. And here, what you notice is that the speed at which for the convergence of this expected value of this average of samples depends on the cross terms and how quickly things get mixed up. And that's one way to in this proof you can start seeing that as the Markov chain starts mixing up as time goes to infinity, the Markov chain is going to start mixing up, and it's going to start going to stationary distribution, and the Markov chain is going to act almost as independent random variables. And the speed of convergence of the average of the samples depends on this mixing time, how fast the Markov chain mixes. And this is where looking at the second largest eigenvalue tells you information about how fast the Markov chain Monte Carlo methods converge to an exact sample. And that's it for now. This is the one lecture for the Metropolis-Hastings algorithm. And in the following lectures, we're going to talk about Bayesian inference. Thanks for